Okay, so good morning, everybody. I have here on the board the definition of the limit that we met for the first time last time, and today we're going to get to know each other better and practice it some more, do maybe one more example, then do some examples where the limit does not exist, and then prove some more theorems using this definition, and we're building up the theory. So let me remind you, we say that the limit of a function f of x is L when x approaches a if for every epsilon, and we said that this is a key word in this definition, for every epsilon we can find a delta such that if x is delta close to a, if the distance between x to a is less than delta, or another way of saying this, if x is between a plus delta and a minus delta, this and this is the same thing, and we added that x is not a itself, then f of x is epsilon close to L, or f of x is between L plus epsilon and L minus epsilon, or f of x is in an epsilon neighborhood of L. And we did many drawings and tried to explain things doing all these kinds of things, and that's just to kind of grasp the idea and get familiar with this. But when we work, we need to work with a formal definition. Okay, so let's start off with another example of calculating the limit. So here's our first example for today. So we want to show that root x approaches root a as x approaches a. Note that this is another way of writing the same thing. You can either use the notation of the lim, the letters lim, which stand for limit in English, or limes in Latin, or you can use this long arrow, and it's the same thing. And we're going to assume that a is positive for a equals 0. There's a tiny issue, so we'll explain it in a minute. So the first thing I want to do is draw the graph. Whenever we have a function, it's always good to right away draw the graph when possible in order to picture it. So this is what root x looks like. Everybody knows that, right? And what we're saying is that if we pick any point A here, there's A, when the x's get closer and closer to A, the values get closer and closer to the value of the function at A, in this case, which is root A. And we said this is just a particular case of a very general theorem that said for any elementary function, the limit can be obtained by just plugging in. Remember we said that? Okay. So, by the way, at the point 0, this function is defined, right? But we cannot talk about the limit at the point 0, because the point 0 doesn't have any neighborhood on which the function is defined. Right? Any neighborhood you take, if we zoom in on 0 here, here's a big zooming in on 0, any neighborhood we take here, any neighborhood, on its left half, the function is not defined. Right? So we can't talk about a delta neighborhood of 0 because the function is not going to be defined here. What we can talk about is what happens when we approach 0 only from the right. That can be done. And then what do the values of the function approach? 0, right? So this is going to be a notion which we're going to define, maybe today, maybe next time, of a one-sided limit, when we approach only from one direction and not from both. Okay? But this is yet to come. So for now, we're only talking about a which is positive. Okay, so we want to show that this holds using the definition of the limit. So how do we do it? We say, okay, let epsilon be greater than 0. Remember? Throw an epsilon at me. I want to show that I can find a delta for which that line in the definition holds. If x is delta close to a, f of x will be epsilon close to L, right? How do I do it? Remember, what was our usual strategy? Right. Start with what we want to show. We want to show that f of x minus L is less than epsilon. So write it down, start working with it, and at some point or another, you're going to see what delta you need in order to guarantee it. Okay? So let's do it. What is f of x in this example? Root x, correct. What is L? What are we claiming the limit is?
0?
No. Root a. This is L. So this is f of x minus L. We want to show that this is small, that this is less than epsilon. Now here there's a trick. There are some standard tricks that we will get used to and show up everywhere in calculus, not just in limit calculations. And does anybody know what the standard trick is? Right. Multiply by what we call the conjugate. Okay? Multiply by root x plus root a. And you'll see why in a second. Okay? But we can't just multiply things. Right. We multiply and then divide by the same thing. Okay? So I'm going to multiply this by root x plus root a. And in order to compensate for that, I'm going to divide it by root x plus root a. Do you agree that I can do this? This is like doing nothing, right? Okay. Now, what do I get? So, what do I get? The bottom, I'll leave the same for a minute. What do I get on the top? So first of all, do you agree that I can put an absolute value on this root x plus root a? Because everything is positive here. So with absolute value, without absolute value, it's the same thing. Do you agree? Right? Okay, so I get root x minus root a, root x plus root a. Right, it's something of the form a minus b times a plus b. Right? And that's a standard algebraic identity, which equals what? Right, this squared minus this squared, and that works wonders for roots, right? So I get root x squared, which is x, minus root a squared, which is a. So this is what I get on top. And when I see this, I'm happy, right? This is precisely what delta can handle, right? Remember? Okay, good. So the only thing that I still have to get out of the way is this x sitting down here, right? I want to write this less than epsilon. That's what I want. In order for the top to be less than epsilon, delta is going to take care of that. This root a is a constant. It's like in previous examples, we got x minus a over 2. And then we took delta to be 2 epsilon. So here, we're going to take, for this root a, we're going to take delta to be root a times epsilon, and the root a is going to cancel. You'll see it in a second. But this x, this is a problem. Okay? Why? Because I can't, x is not fixed, right? X varies. So I can't prescribe a delta that would in any way controlled for root x, because root x is not fixed. But what I can do, and again, this is very standard steps, I can say that this is less than, if I just throw away this root x. Because this thing is something positive. If I make the denominator bigger by adding it, I make the fraction smaller. So if I remove it, I make the fraction bigger. Does everybody agree to this inequality?
Yeah.
Everybody? Good. So now this root x is out of the way. And eventually I want to say this is less than epsilon. And it's okay if I have some inequalities along the way, as long as they go in the same direction. So I want this to be less than epsilon. This equals this, less than this, equals this, less than that, less than epsilon. That's fine. Right? Okay. So now, as we said, we want this to be less than epsilon. What do we take delta to be? Take delta equals?
Epsilon over.
No, multiply by.
Right. Epsilon times root a. Then, if x minus a is less than delta and greater than 0, remember that's part of it, then, and now we can follow our calculation, so if x minus a is less than delta, and delta is epsilon root a, so here we get that this is less, x minus a is less than delta, delta is epsilon root a, so this is less than epsilon root a divided by root a. That's why we took delta to be that, which is precisely epsilon. Okay? So we did 2 examples last time, we did another one just now, and I think you can start seeing the pattern, how we do things, okay? And you should also be able to see that when you eventually look at the proof, at what we wrote, you should see the entire definition of the limit hidden there. And here it is. I'll emphasize it in blue. So take epsilon greater than 0. Give a delta. Then, if x minus a is less than delta, then f of x minus L is less than epsilon. All the rest was just calculations we did along the way. But eventually, we showed precisely the definition of the limit. Take any epsilon. For that epsilon, you get a delta. Delta is a function of epsilon. It depends on epsilon. And then any x in a delta neighborhood of a would satisfy that f of x is in a delta neighborhood of L. Its distance from L is less than epsilon. Good? Okay. So I can see in your eyes, there are many, many eyes here, but I can see some eyes that are already saying, got it. Okay. And by saying got it, you should mean I can try one on my own now. And you should. And I can see some eyes that are still saying, whoa, scary. Then you should see more examples. Okay, and we're going to do gradually more examples. And once again, I'm saying we are not going to we're only touching the tip of the iceberg on this. We're really just getting familiar with it and not learning to actually work everything with this epsilon delta definition. Okay? I want to show you now several examples where the limit does not exist. Okay, and how we see that. So here are some examples. So let's call this example number 1 for today. And here's example number 2. So I'm going to take the function f of x equals bracket x. Remember this function? Let's quickly draw it. Remember, it's this step function that rounds up to the nearest integer from below. any number. Okay? By intuition, just one second, okay? By intuition, at what point do you think that this function will not have a limit?
The integers.
Right, the integers. So whenever you take an integer, for example, let's take 2 here. This is 2. This function is not going to have a limit when x approaches 2. Okay? Let's see that. Let's see why this is true. I'm not going to formally write why the definition doesn't hold. That would really make half of you run out of the class. Okay? I'm going to explain it intuitively, and maybe we'll get to writing why definitions don't hold a bit later, because that's even more of a mouthful. Okay? So what happens at this point 2? In order to say that there is a limit, we want to say that when we get closer and closer to 2, the values get closer and closer to some L, right? But when we get closer and closer to 2, we're either getting closer and closer from the right or closer and closer from the left, right? If we take an x that's close to 2 from the right, what's the value of f? It's 3. No, it's 2, right? If we're close from the right, this is 2. This is 2, and this is 1, right? So if we take an x that's bigger than 2, 2 point something, the value of f is going to be 2. No, we round to the greatest integer from below. Okay? So if we take 2 point something, we're going to get 2. No matter how close we are. No matter how close we are to 2, the value of f is always going to be just 2. Do you see that? On the other hand, if we're close to 2 but from below, from the left, 1 point something, the value of f is 1. So no matter which, let's zoom in on this, zoom in on 2 here. Here's 2. We zoomed in, and here's the picture at 2. By the way, there's a full bullet there indicating that the value of at 2 itself is 2, and the value at 2 is not 1. Okay, do you understand what I meant by this, this hole in this bullet? Okay, so take any neighborhood of 2. Let's use another color. Take any neighborhood of 2. Doesn't matter how small it is. You're going to have x's with value 2, and you're going to have x's with value 1. You can't guarantee that if you're close to 2, all the values are close to some L. They're always going to be apart. They're always going to be some near 2 and some near 1. Do you agree? So the limit does not exist in this example. Okay, so let me write that. There is no limit at any a which is an integer. Questions? Very good. Okay, so we didn't define one-sided limits yet. We're going to define them. But this is a classic example where you have one-sided limits. If you approach 2 just from the right, then everything is fine. The limit is 2. Right? If you approach 2 just from the left, then the limit is 1. Okay? But we didn't define one-sided limits yet. We'll get there. More questions? Yes?
That means that by definition, there is no neighborhood that for all x this will give me the same.
Okay, so let me try repeating what you said.
I'm trying to find the right definition. I don't know.
Right. You're trying to read out the definition and to read it out in how would it read in order to say there is no limit. And that's exactly what I said I don't want to do it now. Okay? Because it's harder. It's harder. Okay? I just want to convince you that the way it is written, it doesn't hold. If you believe that, I'm happy at this point. Okay? Trying to reverse it in order to, how would it formally be stated in order to say that there is no limit is harder, and I prefer not to get into that, not to go along that path at this time. Okay? Is everybody convinced? Yes?
Can we go to the last example?
The previous example. So maybe ask me about that over the break, okay? Because I prefer to continue and not backtrack. Let's do another example where there is no limit. 3. Let's look at the function f of x equals 1 over x. Again, let's draw it. What does 1 over x look like? Right. That has a name, that shape. Do you know what that's called? Right, it's in hyperbola. So it looks something like this. And this you should know. This you should know well. How to draw these graph of these standard functions. At any point where this thing is defined, you can see that there is going to be a limit, right? At this point here, maybe, as we approach it, the values of the function approach the value at that point, right? And we know that because we remember we had a spoiler last time. We said any elementary function, at any point where it is defined, the limit is just obtained by plugging in that point. Where is there an issue here? At 0. So at the point 0, at the origin, this function does not have a limit. Again, there's this two-sided phenomenon. When you approach 0 from the right, the values of f do what? Go up and up and up and up and up, get bigger and bigger, right? True, that's going to have a name a bit later. We're going to need to define it, and we're going to say they tend to infinity. Okay? But we didn't define that yet. As we approach 0 from the right, what happens here? The values of the function do what? Right, they tend to negative infinity. So there is no L such that if we're close enough to 0, the values of the function are all concentrated near L. Okay, this is like the most unconcentrated picture you can imagine, right? As we get closer and closer to 0, these things run off from each other as if they really don't like each other. Do you see that? So do you agree to the statement, there is no limit at a equals 0? Everybody? Good? Okay. Let's do another example of where there is no limit. You know what? Okay, before I erase this example, I am going to return to it because I wanted to say one more thing, which I forgot. Let me rewrite what we were doing here. We were doing the limit of root x as x approaches a is root a. Okay, and then I'm going to take your question too, since we're back to that example. So I wanted to point out one thing. Two things, maybe. So the first thing is that we're dividing here by root a. Do you see that? Whenever we divide by something, we have to, just for a second, take a step back, look at it. Our hand should shiver. We should verify that we're not doing something forbidden, that we're not dividing by 0. Okay? Are we dividing by 0 here? Is there? No. Why not? Right. We assumed that we're only dealing with positive a's. Okay? So that's one thing. Another remark about this example is that there's a tiny point of delicacy that I kind of hid, and I want to now reveal it. We said here that we're taking delta to be this thing, epsilon root a, whatever that is. It depends on epsilon and it depends on a. If a is 1 and epsilon is 1/2, then root 1 is 1 times 1/2, then delta is going to be 1/2. Do you agree? And what does it give us? It gives us a neighborhood of a, from a plus delta to a minus delta, a neighborhood of a, in which we can guarantee this thing, that the distance from L is less than epsilon, right? But in this example, there's something, a point of caution, a point where we have to be careful. If for some reason somebody gave us a big epsilon, like for example epsilon equals 100, okay? And suppose a is just 1, okay? So what is 100 root a?
100.
It's 100. Do you agree? So that naturally, when you give a big epsilon in order to guarantee things, you're going to need a big delta, right? So if we just do this, we're going to get delta equals 100 if epsilon was 100 and a is 1. Do you agree? What does that mean? It means that if this is 1, the neighborhood is going to be over on that board. Okay, so let's not say 100, let's just say 3. Otherwise, I need long arms. So the neighborhood we're going to get is not a small neighborhood. We're going to get a very big neighborhood. A plus 3 to a minus 3. Do you agree? This is going to be the delta neighborhood of a, right? But here something went wrong. We're into the forbidden zone. We're out of the domain of the function. We can't say anything about x's here because f is not defined for x's here. Do you agree? So somehow we have to rule out the possibility of getting delta neighborhoods which pass 0 to the left. Okay? Do you understand the issue? Do you understand what the problem is? And the way to fix it is standard. We're just going to say here, take delta, not just to be epsilon root a, but check what you get. If delta is small enough, meaning if delta, what's the biggest delta can be in order for this not to happen? A itself. If delta is a, that would get us exactly to 0, to here. Do you agree? Anything bigger than a would exceed 0 to the left, and we're in trouble, right? So the statement is going to be, in order to fix this, I'm going to replace this. Maybe I'll do it. I'm going to replace this and say, take delta to be the minimum value between a itself and epsilon root a. This means you do the following. You take your epsilon. You calculate these two numbers. If epsilon root a is less than a, then that's the minimum, and that's going to be your delta, and everything works fine. Do you agree? If a is less than epsilon root a, which is if epsilon root a was too big, and you want to make a smaller in order not to go out to the illegal area where f is not defined, then just take a. It's still going to be smaller than this, so this inequality will still hold, but you know you're safe. Okay? So this just shows you even in more, puts in light even more the fact that working with this definition is hard. Yes?
But then, what connection do we have between delta and epsilon if we say that
Delta depends on epsilon. Okay? It's at most this thing, and we saw that being at most this thing guarantees what we need. It may be smaller if this happens to be smaller. Okay?
If we say that delta is equal to A, then how do we have that?
We first check. We check what this thing is. If this thing is bigger than A, then we say, okay, let's just be happy with delta equals A. But then we know that A is less than this thing, and therefore this is less than this thing. So it still holds. So epsilon is not, we can't just say take delta to be A. That won't work. That won't allow this step. We have to guarantee that this is less than epsilon root A. Okay? Yes?
Okay, so see how it says on the board absolute value of x minus a all over root of a is less than epsilon. Why do we want it to be less than epsilon?
So the answer, the question was, why do we want this to be less than epsilon? That's the definition. What I highlighted in blue here is precisely the definition. We want f of x minus L to be less than epsilon. Let's look at the previous board a second. There it is. That's what we want. That's what we want to show. That if x minus a is less than delta, look at this board, please. Please look at this board for a second. Where's Yair? Did he fall asleep? Yair! Thank you! The definition says if x minus a is less than delta, we want f of x minus L to be less than epsilon. That's the definition. That's what we want to show. That's precisely what we're doing. Sorry. And if you look back at the previous examples, which we did last time, that's what we did there too. Okay? Okay, so now I can erase this and put some more examples. And the examples that I want... What? More questions? More questions later, okay, over the break. I do want to move on as well. I want to answer all your questions. I always want to answer all your questions, but I'm going to have to at some point, put a pause, say more questions a bit later, and move on, because we have to cover the material as well. Okay, so never be offended from that. Just remember your question and come to me over the break, and we'll try to answer all the questions. And if over the break I hear a good question that I think is very important that everybody hears the answer to, I'll mention it at a later time. Okay, so we're now at example number 4. Here's another example where there is no limit. F of x equals 1 over x squared. So 1 over x squared looks like, I hope everybody knows this, looks like this. Right? You all know that. Where is there an issue? At 0 again. And what happens at 0? When we approach 0, either from the right or from the left, what happens to the values of the function? Right, they get bigger and bigger and bigger and bigger. Okay, so let's maybe emphasize that by doing something like this. Do you agree? This will have a name. A bit later, we're going to define this as saying that f tends to infinity as x approaches 0. But as far as the definition of the limit, which we already wrote down, goes, this function does not have a limit at 0. Okay? So we're going to reserve the words that f has a limit only for finite limits, only when L is an actual number. And in this case, we're going to say that it does not have a limit. We are going to say later that it tends to infinity. Okay? But the words has a limit, those words are going to be only for finite limits. So, f does not have a finite limit at a equals 0. Good?
Shouldn't we say the same for example 3?
Well, example 3 was 1 over x, and in that case, it doesn't have a limit and it doesn't tend to infinity either. From either sides, we had different phenomena. We're going to discuss that. We're going to discuss one-sided limits. Okay, that one went wrong completely. This one seems to have some limit phenomenon going on, and we're going to say that. It's just not going to be called a limit. It's going to just be said to go to infinity. Okay, to tend to infinity. Next example. The next example is maybe the most intriguing one, especially the first time you see it. So the function I want to draw, I don't think we met this function yet, is the function sine of 1 over x. Sine of 1 over x. This is a composition of functions, right? And let's try to draw it without any full investigation of functions, right? We're not going to take derivatives and find maxima and minima. We're just going to try to decipher it off the formula very roughly. So first of all, this is sine of something. It's bounded between -1 and 1. Does everybody agree? Okay, so I'm going to draw 1 here and -1 here, and I know that the function cannot exceed this lower and upper bound. Does everybody agree? Okay. Now, how does it behave? Let's think for a minute. Okay, it's going to behave, it's going to have this wavy behavior because it's a sine, but let's try to be a bit more precise than that. So, what happens when x gets bigger and bigger and bigger? When we head off to infinity and beyond? Right, 1 over x gets smaller and smaller, tends to what? To 0. Do you see that? So as the x's get bigger and bigger, 1 over x gets closer and closer to 0. What's the value of sine at 0? 0. So as x's get bigger, this whole thing should approach 0. Do you see that? Okay? So just intuitively, as we get further out, we should see some phenomena like this, of approaching 0. Do you agree? Likewise, when we approach negative infinity, when the x's get bigger and bigger and bigger, but negative, 1 over x gets smaller and smaller and smaller, still close to 0, right? And therefore, sine of it is still going to approach 0. Do you agree? But from below, from negative numbers. So we're going to see this phenomenon on the negative part. Okay. Now, what's going to happen in between? As the x's get closer and closer to 0, as the x's get closer and closer to 0, let's say from the positive part, what happens to 1 over x? It gets bigger and bigger. Do you agree? Does everybody see that? As the x's get closer and closer to 0, 1 over x gets closer and closer to infinity. Do you agree? So, how does sine behave as we go off to infinity? It just oscillates, nice and calm, right? So all these oscillations should somehow happen as we get closer to 0. Okay? When the x's get closer to 0, sine of 1 over x should behave the way sine x behaves as we head off to infinity. And the way this looks is precisely that. These oscillations start happening, and they just get they just get closer and closer
Why?
until, well, no until. They just get closer and closer and closer as you approach 0. Think of an accordion. Do you know what an accordion is? That's what happens. And in fact, that's the same thing that happens on this side as well. So the picture is something like this. Okay? And that's what the graph of this function looks like. Okay? Is everybody convinced that this is kind of what should happen?
Yes, let's have.
Okay? So, by the way, what happens at 0 itself?
Zero.
Not defined. It's not defined at 0. Okay? Does this oscillation that gets squeezed into the y-axis, does it ever reach anything? Does it ever? No, it just keeps oscillating forever and ever, getting closer and closer. Okay? And that's something hard to grasp when you first encounter things like this. It's like, it's kind of similar to the ability to get closer and closer but never reach something. So maybe an intuitive example of such a phenomenon, just something to open your mind, is suppose I want to walk towards this table here. Okay? And at each step, I'm going to go half the distance. Okay, so here, I went half the distance to the table is here. Half the distance to the table. Now the next step, I'm going to go half of the remaining distance. Okay? And in the next step, I'm going to go half of the remaining distance. Am I ever going to reach the table? Never going to reach it. How close will I get? Very close. Infinitely close. Never going to reach it. Do you agree? Okay? So the same thing happens here. These oscillations get, well, they're always between -1 and 1, but they get shorter and shorter, or more frequent if you want, but they never reach. There's no such thing as reaching. That's kind of depressing, isn't it? But that's all the fun in calculus. Okay? Question.
If you have a line with a hole in it, the limit of that hole exists, right?
If you have a line with a hole in it, the limit of that hole is this.
Exists.
Exists. What do you mean the limit of the hole?
Meaning the limit of the x value at the hole.
If you have, okay, so you're asking if you have a straight line,
Yeah.
that's the graph of a function, you mean,
Yeah.
and it's not defined at some point,
Right.
and you're asking, does the limit exist at that point? Is it the value at that hole? Okay, got the question. Yes, the answer is yes.
So, but it never.
But here that's not the situation. Okay? It's not that if you, suppose we have this amazing microscope, that we can zoom in on this with amazing resolution. Amazing resolution. Now we're very, very close to it. I don't know if you can see how close we are. Okay? But -1 is now way out of this picture. -1 is way down there. And 1 is way up there. And you're asking, what are we going to see? Okay? Here's what you're going to see. You're going to see this. That's what you're going to see. Okay? Infinitely many oscillations getting closer and closer to each other as they approach the axis. You're not going to see their tops and bottoms because they're way out of your frame. But that's what you're going to see. You want to zoom in closer? Go ahead. Be my guest. You're still going to see that. Okay? Never going to reach. Gotta get used to it, right? It's not, doesn't come for free. Yes? Question?
No. So all this is happening before 1, going to the right, correct?
Before?
1?
You're asking where is this first?
Yeah.
Okay, so we can actually calculate it, right? Where does sine have its peaks? at multiple, sine itself looks like this, right? And its first peak is at pi over 2. Do you agree? So the first peak of this thing is going to be at 2 over pi. Because then 1 over 2 over pi is going to be pi over 2. So this peak, if you want to pin this one exactly, is at 2 over pi. That's the value where... And any x bigger than 2 over pi, 1 over x is going to be smaller than pi over 2, and therefore there's not going to be any other peak. It's just going to tend to 0. There it is, tending to 0. Do you see that? But then as you get bigger and bigger x's, every time x hits pi over 2 plus a multiple of 2 pi, 1 over it is going to get a peak. And they become closer and closer. Okay? Wow! Why did this show up? What are we discussing at all? Limits, remember? So at any point which is not 0, this is just an elementary function, right? It has a limit. If you ask me about this point here, there it is. The limit is this, if this is a. Do you agree? Where is there an issue? At 0. And at 0, it's not going to have a limit. Okay? Why? Because no matter how close you are to 0, you cannot guarantee the values of the function, the f of x's, being close to any L. No matter how close a neighborhood you take of 0, the values are always going to oscillate between -1 and 1. Do you see that? So this function has no limit at a equals 0, despite the fact that it's bounded. So what messes up the limit is not the fact that it goes to infinity or negative infinity or something like that. It's just that it doesn't have a limit. You can't force it. You can't force the values to be in any neighborhood of any number. They always oscillate. Yes, question?
At 0, doesn't it still pass through the order?
It's not defined at 0. It doesn't have a value at 0. Right? Do you agree that this thing doesn't have a value at 0? You can't define it at 0. You would be dividing 1 by 0. That's not defined. Okay? When you reach 0, that's your question? You don't reach 0. It's the same question as the table. Okay, I'm getting closer and closer to the table. Don't I eventually get there? No. If what I'm doing is walking each step half of the remaining distance, I'll never get to the table. Okay? That is mind-boggling. That is something that... Okay? Take a little child, try to explain that to him. He's just not ready to absorb something like that. Sometimes they are. But here we have to kind of open our minds and get used to... For some people it's easy. Some people say, oh sure, why? I believe that. I can live with that. Some people have this resistance and have to get over it if you want to do calculus. Okay? That's the whole point of limit. The whole point of limits. You never get there. There is no such number infinity. Okay? Okay. So we just saw many, many counter examples. I want to remind you now, I have it written down here. I wrote it before class started. This is the theorem that we ended with last time. It's called limit arithmetics. Remember what our goal is. We don't want to have to go to the definition of the limit every time we do a calculation. That's crazy. Okay, we want to be able to do calculations using theorems. To have a good theory that would allow us to calculate limits without actually doing epsilonautics every time. And this is a key theorem, limit arithmetics. If you have two functions, then their sum goes to the sum of the limits. Their product goes to the product of the limits. The quotient goes to the quotient of the limits. We'll have a break now. After the break, I want to prove one of these. I think I'm going to do the number 2. Okay? And then we'll see some more theorems. So let's have a break.